started. Today we have a presentation from Jim Worrall, who works the Colorado Forest Health Protection Program in Gunnison, Colorado. Jim received a PhD in plant pathology from the University of California, Berkeley. After postdoctoral work at Göttingen University in Germany and at the University of New Hampshire, he joined the faculty at the SUNY College of Environmental Science and Forestry in Syracuse, New York. He served there as assistant and associate professor before joining the Forest Service, where he is now a forest pathologist with the Forest Health Protection in the Rocky Mountain region. So thanks again, everyone, for bearing with me with the technical difficulties, and I will hand the floor to Jim.
Okay, thank you, Megan. Hopefully everybody can hear me okay. A little bit of an awkward way to give a seminar the first time, but we'll see how it goes. I think there's also an opportunity for SAF credit as well as ISA, so maybe that can be covered at the end if anybody wants SAF credit. So what I want to discuss today is the title that you see there, a strategy for forest adaptation to climate change, with a case study of Aspen and Spruce in southwestern Colorado. So what I'll do is give you a little background, how we got into this project, what happened to our forests, and what the local national forest is doing about it, and then ways that we think we can not only address what's going on in our forests today, but also address making them more resilient to future climates as well. And I need to make sure to point out that these co-authors here have a lot to do with this, and especially Jerry Rayfelt and Nick Crookston played a key role, really the modelers behind this effort, and certainly wouldn't be possible without them. So around 2004, on the San Juan National Forest in southwest Colorado, foresters, namely Phil Kemp, began to report increasing levels of damage to aspen that was not the usual kind of stand-level damage that we're used to seeing. So this damage was part of what we later named sudden aspen decline. It was characterized by, branch dieback, so dying of individual branches in the crown, usually from the tips, thinning crowns, and eventually mortality. It also, as I mentioned, it occurs on a landscape scale, not at the individual stand scale that we're used to seeing this kind of mortality happening at. And there's also a lack of involvement by primary insects and pathogens that are known to kill vigorous aspen. So there wasn't any of the traditional damage agents that we are used to blaming aspen mortality on. Okay, I did something wrong there. Megan,
okay, hold on.
Yeah.
Here I am. Here I am. I don't know what happened, but we'll just...
I hit the space bar instead of the right arrow.
No worries.
Sorry, folks. Pay no attention to what's going on behind the curtain. Okay, luckily we're just into the first few slides here. So yeah, over the next few years it spread to many areas of aspen in Colorado. It was especially severe at low elevations. You see the sagebrush surrounding this dying clone here, and also on south-facing slopes. So In some stands, there was nearly complete mortality. The average in affected stands was a little over 50% mortality. By the time it was over in the southern Rocky Mountains, over 500,000 hectares were affected, primarily in Colorado. In this map, the red shows the areas of decline, and there is a buffer around them to make the small polygons visible. The blue and the green show the change in climatic suitability for aspen, and I'll explain that later, during the decade that accompanied this episode. So the blue shows a decrease. That's where most of the decline occurred, and the red or the green shows an increase in suitability. So this all started just 2 years after the peak of the turn of the century drought, and there's really overwhelming evidence to support that drought as the primary inciting factor for this damage. And a lot of species were affected, not just aspen, by this drought. So this drought was really the peak of a long-term drying trend since the mid-1980s. The upper graph shows a dryness index, and the lower graph shows a moisture index, the middle one that is. So they're opposite. So I think it's really informative to put this drought in perspective while considering the level of damage that it caused. So a group of climate scientists, Schwalm et al., you see at the upper right-hand side there, they studied this drought in western North America and came up with some startling results. First, in the context of the past, they found that you had to go back over 800 years to find a drought period that was severe as this turn-of-the-century drought. So that drought was pretty severe. Then, in the context of the future, this graph shows the last century based on actual weather records. It shows the turn-of-the-century drought, that little blip in the middle with the arrow, and then a projection of the rest of the century based on these global circulation, general circulation models. Now that little blip doesn't look so bad anymore when you look at it in the context of the projected future. In fact, the future looks a lot worse. So these authors stated that by the 2030s, not too far away, moisture conditions during the turn-of-the-century drought will become the new norm in western North America. So that'll be the normal condition. And then they further said that toward the latter half of the 21st century, the precipitation regime associated with the turn-of-the-century drought will represent an outlier of extreme wetness. Extreme wetness, that's startling. But that drought, the worst one we've seen in 800 years, it had a pretty huge effect on our forests in Colorado and surrounding areas as well. We had the massive mortality event in pinyon pine that was associated with the IPS outbreak, clearly directly tied to the drought. We had sudden aspen decline, which I described briefly to you. We had the mountain pine beetle outbreak in northern Colorado and southern Wyoming, which, while not entirely due to the drought, certainly was facilitated by it. And now, mostly in southern Colorado, we have the spruce beetle ramping up now. And again, stand conditions and triggering events play a role there, but the drought also plays a role in making trees more susceptible. So when you look at what that little blip in the middle of this graph did, can you imagine what the rest of the century will look like in terms of the impact on our forests? It's pretty tough to imagine, I think, and that's where the bioclimate models come in. But before we get into the bioclimate models, I wanted to say a bit about climate change and the dilemma that it poses for forest management. So we all know that climate change is a looming problem and needs to be considered in forest management. And I think by and large, all of the forest managers that I've come into contact with and discussed this with would take that point of view, that it's something we need to be looking at and planning for. And in fact, the Forest Service requires consideration of climate change in planning. But more importantly, we have to realize that if you don't plan for the future, you're planning for the past. So everything that we do, not only in forest management, but also in, if you're building a house or whatever you're doing, you are implicitly anticipating what the future is going to be like, and you're creating that plan for that will be suitable in those conditions. And so, in the past, we've always just assumed that the future was going to be like the past, and that's been fine. We didn't even think about it really, because we don't think, okay, now the climate that I'm expecting for this stand when I do this treatment is such and such. No, it's just going to be the same as it's always been. Well, that doesn't work anymore, so we have to consciously anticipate what the future climate is going to look like and make sure that what we do on the forest is going to be compatible with that. So really the alternative is ecological havoc. We know that climate change is going to be a lot faster than the capacity of the ecosystems and the plant communities to adjust, either genetically or by migration. And if we don't do something to help the ecosystems adjust, they will adjust on their own, but it's going to take a long, long time, hundreds of years, more likely thousands of years. And the ecosystem services that we depend on will be degraded during that time, and loss of biodiversity for a long period. So I see Floyd has a question there. Do you have any geographic areas modeled according to precipitation? We haven't considered precipitation alone, but both precipitation and temperature and many different climate variables that are derived from those as they change over the seasons and interact and so on. And I'll show you the modeling in a little bit. So as far as forest management, I think it's been a tough problem. The climate change is huge. We know that there's a lot of uncertainty about it, and that uncertainty can be paralyzing. It's also something we've never had to deal with before, and so most managers are not trained for it. And let's face it, we have a lot to do just keeping our heads above water without dealing with the biggest problem the world has ever faced. And then, I think part of it too, in the Forest Service at least, is there's sometimes too much information on climate change. We get emails frequently with links on climate change and information on it, links to climate change studies and data about it. And to help in dealing with climate change, to help managers, there's this steady stream of conceptual approaches that are produced, and strategic frameworks and tools for analyzing goals for climate change and systems for information needed to develop plans. And that's all well and good, but we don't have really many concrete examples of how to develop an actual practical plan. And that's what we're hoping to develop here. So I want to now cut aside a little bit and talk about what's been going on in the Grand Mesa, Uncompahgre, and Gunnison National Forests, and tell you about a case study that we're working on with that. So the GMUG, what we call it for short, is in southwest Colorado. Wide range of elevations. The eastern and southeastern portions of the forest are bordered by the Continental Divide, and goes all the way out in the Uncompahgre Plateau, sticking out into the desert there on the west. So a lot of not only diverse topography, but diverse forest types as well, like most of the mountainous west. And the two most abundant cover types that we have, the forest cover types, are aspen and spruce fir. Well, we had a lot happening with our aspen and spruce fir recently, as I briefly mentioned. Sudden aspen decline affected about 33% of the cover type, the aspen cover type on the GMUG, and damage stands continue to deteriorate. I don't want to spend too long on these slides, but this is from a remeasurement of plots that we originally did in 2007, and find that let me get the arrow here. So, yeah, the arrow doesn't want to follow me, but it's the left side. You see the healthy plots. They did not change much between the gray, the old measurement, and the white, the new measurement. Whereas the sick plots went down quite a bit in live basal area aspen. They also decreased in recently dead basal area, but that recently dead basal area is still much higher than it is in the healthy plots. And then snag basal area increased. And recent crown loss also decreased a little bit since the peak of SAD in sick plots. But again, still in the sick plots, you see it's still much higher than it is in the healthy plots. So those stands are continuing to deteriorate, and regeneration is slightly decreasing as well. In the healthy stands, it's actually gone up on average, and this is like a histogram, equivalent of a histogram here. You see that we have, in 2013, we have in healthy stands fewer plots that have low numbers of regeneration, low density, whereas in sick stands, the number of plots with low density of regeneration has gone up. So the second major event in the forest has been in the spruce fir and the spruce mortality. The spruce beetle is in full swing here. It's just been coming over the Continental Divide from the Rio Grande National Forest in the last couple of years. And these watersheds like this have really high mortality levels. About 99% of the mature overstory affected in these stands. This is the Colorado-wide progress of spruce beetle over the last 15 years or so, still increasing. And here's a map showing this year's aerial survey result in blue, and the previous year's also. So you see from the Rio Grande, it's just come up. Let me try that arrow again. Okay, here we go. So from the Rio Grande, it's just come over the Continental Divide into the Gunnison National Forest, and it's also been active on the Grand Mesa, too. So the forest has decided to develop a Forestwide Programmatic EIS called the Spruce Beetle Epidemic and Aspen Decline Management Response, or SPEEDMR for short. Lovely name. So the idea is to treat somewhere around 100,000 acres over a 10-year period of spruce and aspen. This would include both mechanical treatment and fire. And the goals are in spruce to remove hazard trees along roads, to salvage, and where possible to increase resilience to spruce beetle in the future. And for aspen, the goal is to regenerate deteriorating stands and increase drought resilience. So, with the goals of the forest and the modeling that Jerry Rayfelt had been doing, we saw an opportunity to apply this modeling here to forest management. So let me first describe what bioclimate models are. They basically describe the bioclimate conditions suitable for a species, and they're basically define the climatic ranges that species can occur in. The way you build the model is you have many points of known presence or absence of the species. So you have points where you know it's either there or it's not, and you can map the associated climate. And then you can represent the distribution.
Hey Jim, before you get into the modeling, I saw a question. I just wanted to draw your attention.
Have any SAD affected stands burned since dieback? What were the outcomes? Will fire help regenerate sad aspen? I'm sure some have, but we have not actually studied the overlap of recent fires and sad. But from everything we know about it, and I'm going to talk about aspen recovery in a little bit, fire should be a great way to turn those deteriorating stands around, as long as they haven't lost too much live basal area. So it will certainly help regenerate sad aspen in most cases, but the result might not be so good when we've lost the majority of the basal area. So hopefully that answers your question. So getting back to the bioclimate models, we can then use the models to represent the distribution of the species as a function of climate and see how good it does at actually predicting the current distribution based on the past climate. And actually they do an amazing job, as I'll show you in a minute. And then by applying future climate to them based on these general circulation models, we can project the distribution of suitable habitat into the future. Of course, this has some of the vagaries and uncertainties of the climate models themselves, the emission scenarios that you use to plug into the models to tell them how hot it's going to get, and the bioclimate model itself. So in order to work on this case study, Jerry Rayfelt developed an aspen and spruce model specifically for the GMUG based on GMUG presence and absence data, and developed a 90-meter resolution mapping system for it that makes it much more useful for management, and also incorporated aspect and slope in addition to climate as factors to identify the habitat. So the hope is that the changes in suitability that we can detect through this modeling can allow today's managers to take the projected future into account. So here's the results based on the reference period for Aspen. So the reference period climate was used to generate a distribution map of the where the climate and topography, by the way, is suitable for Aspen, and that's shown here in green. I guess it's green. I'm a little bit of colorblind, so if it's not really green, you'll figure it out. And then, so it's predicting it outside the forest boundary as well as inside, but we're only comparing it to the actual distribution inside the forest boundary where we have good distribution data. And that the actual distribution there is shown in blue. So where you have the overlap of the actual distribution and the distribution that the model is predicting, that's that teal color, which is most of what you see inside the forest. You see a little bit of blue here and there where Aspen is present, but the model didn't predict it. And you see little bits of green here and there where the model predicted it to be present and it isn't. The latter is easier to explain as possibly just disturbance history, but the other one is pretty obviously an error of the model. But it's pretty minor. You can see that in the big picture, the model does an excellent job of predicting where the climate and topography will be suitable for Aspen. So then, I don't want to get too deep in the weeds here, but want to have full disclosure how this was done, and show you the process for projecting this into the future. So we used 3 GCMs, these climate models that are used by the IPCC, and there's actually like 28 of them in their large group, but we used 3 of them, and we used 3 of these emission scenarios, basically is what they are, these RCPs, kind of a low, medium, and high. And there is, some of you may know, an even lower emission scenario than this, but we excluded that as unrealistic. So anyway, so those 3 the combination of the climate models and the emission scenarios makes 9 combinations. So we had 9 climate projections which were downscaled, and each one was run through the bioclimate models. And so there's 9 different outputs then, and we averaged the outputs of the bioclimate models to generate these projections. So this map shows the difference between the reference period suitability and the suitability around 2060. So the what it is simply the future suitability subtracted from the current or reference suitability, and so that the change is in this color gradient. So the magenta shows a decrease in suitability, and the green shows an increase. So you can see, for instance, on the trying to work this pointer here. On the Uncompahgre Plateau here, it's all negative because the plateau is at an it's a flat mountain and not high enough, and it's surrounded by desert. The Grand Mesa has some increases on the top where actually Aspen is currently not present, and it's mostly present around the margin of the Grand Mesa, the edge. And those margins are decreasing. Otherwise, you see a lot of green in the high mountains along the Continental Divide and so on, and magenta at lower elevations. So the way we do this now, the difference alone is pretty hard to deal with. and you really don't know where it started and ended. So we developed these change zones. Not sure that's the best name for them, but it also uses the difference in model output between the reference and the future period, but it classifies the change. So basically, the model output runs from 0 to 1. 0 is the absolutely no chance that the climate will be suitable for Aspen, and 1 is very likely. And then, so to classify habitat as lost, it was greater than 0.5 in the reference period, and 0.5 is a very good threshold, as you saw in the reference map that I showed you earlier at predicting where Aspen is going to occur. So if it's greater than 0.5 in the reference period and less than 0.3 in the future, we categorize that as lost. And so that's a conservative way to look at it, because if it's less than 0.3, it's quite low. So yeah, we wanted to be conservative about projecting lost habitat. And then the threatened is in that in-between area between 0.3 and 0.5. So it's decreased below 0.5, but it hasn't got quite to the loss threshold yet. Persistent, it remains above 0.5, both in the reference period and in the future. And then emergent habitat is where it's currently not suitable below 0.5, and it increases in suitability in the future. So then the next step is to develop management tactics and apply them to change zones where they will be most effective. So it's not like one size fits all, but we can adjust our strategy into these different zones so that we're doing the right thing in the right place. So here are the change zones for Aspen for 2060. And so the red is lost. We have again on the Uncompahgre Plateau, you know, where it was all going downhill. We have mostly lost with a little bit of threatened in there. On the Grand Mesa, we can see the southern flank of the Grand Mesa is mostly lost. On the the northern edge, it's a mixture of threatened and lost. And that's where the topography comes into play, because the model is recognizing the difference between north slopes and south slopes. And but you notice we don't have any emergent on the Grand Mesa where there was an increase in suitability, but it wasn't enough to get above the 0.5 threshold. And then we do have a lot of emergent closer to the Continental Divide and the high elevations. But of course, as we know, a lot of that is not going to be suitable for other reasons, rock and so on, unstable slopes. So what can we do with this? Let's talk a bit about Aspen again and management of Aspen. We can use mechanical disturbance or fire to accomplish two objectives. One is resilience to basically, we know that younger aspen is more resilient to drought, so if we regenerate mature aspen, we'll be increasing the resilience of the population as a whole. And then recovery, we know that we can regenerate. There's a big question there. Maybe I can hold that one till the end there so I don't get too sidetracked. Yeah, recovery, we can regenerate the SAD-affected stands before we have too much canopy loss, as I mentioned before, and I'll show you how this makes sense here. Here's another question. Yeah, I did talk about, Megan, I did talk about the emission scenarios. There were 3 different emission scenarios that we used and averaged. So if you're familiar with the RCPs, these are 4.5, 6, and 8.5. And I might as well check out this other question here too. I assume you can all see this question, so I won't read it out loud. Yeah, that's kind of lengthy. I think if you don't mind, I'll wait till we get to the end to look at that. So the reason we pretty sure that the younger stands are more drought resilient is because during the turn of the century drought and following it, the younger stands, and the one that you see in this picture here was about 35 years old. Stands below about 40 years old were unaffected and often surrounded, this is a patch cut of aspen, often surrounded by dead and dying residual overstories. So in this case, it really is pretty clear that the age diversity is increasing the resilience of aspen to sudden aspen decline, to drought. And then the cutting, bringing it back after it's dying, sudden aspen decline, declines in general. And this was a study that was done in Utah at Cedar Mountain, which Paul Rogers is certainly familiar with. And so Ohms did a thesis on this. They had mortality at an earlier stage there, and they harvested at different levels of mortality, and below about 50% mortality, there was a good response to the harvest in terms of sucker production. Above 50%, it didn't look too good. The same thing was done in Utah, in Colorado rather, or a similar thing. Wayne Shepard and Skip Smith just finished a study really on the GMUG that showed that again, if you have pretty good, very good regeneration response when there's low to medium, and less when there's high amount of mortality due to SAD. So these are indications that we can bring it back as long as we don't wait until it's deteriorated too far. And where do we apply these treatments to increase resilience and to aid recovery? In the lost zone where we don't expect aspen to have a bright future, these are not places where we would want to invest in resilience or recovery treatments. We would only treat for short-term benefits of other sorts, like wildlife or some such. In the threatened zone, this would be a good place to do resilience and recovery treatments here to increase the likelihood of aspen survival in future droughts. In the persistent zone, normal management could go on, if normal management actually ends up being a resilience treatments anyway, so it's all good. And then there are opportunities for facilitating migration of aspen. So if we're in a persistent zone near an emergent zone, we could favor existing aspen there where it's, say, being got scattered aspen and conifers. And then in the emergent zone, we could consider disturbance treatments to create seed beds for facilitating migration. So here's how that would work. And the reason I mentioned persistent zones, because you have to have a seed source, and that would obviously be in the persistent zone. So let's say we have, as we have here, scattered aspen that's being overtopped by conifers. And this is in an area where it's pretty close to the emergent zone, and it's upwind, so the wind would take the seed there. So this would be a good place to do some treatments to increase the amount of aspen there, assuming it's a female clone. And over several decades, you would get mature aspen in there that could provide a seed source. Then when the climate is right, you could make sure that either wildfire or human-caused disturbance of some kind creates the disturbance and opportunity for seedling establishment there, and then let nature take care of the rest. So as far as spruce, we have a lot of spruce in the threatened zone, in that netherworld where it's kind of on the edge. In the plateau, again, spruce mainly looks like it's not going to have a lot of good habitat. Some threatened scattered in there, mostly threatened on the plateau, and much less emergent. And what there is of emergent habitat for spruce is probably not going to be suitable for other reasons. So we're really looking at some persistent along here and a lot of threatened. So what can we do with spruce in these areas? Certainly type conversion is a consideration. We can favor or plant drier types such as Douglas fir, blue spruce, lodgepole pine, and there are places where the aspen emergent zone overlaps with the spruce lost zone, so those could be places for aspen establishment. Resilience treatments would be focused on reducing basal area and getting younger, even-age stands, and planting in areas that are threatened or persistent, climate-based seed transfer guidelines, and certainly salvage is something that is of great interest on the GMUG. And where can we do those things? Here we have the zones again, and we wouldn't want to do those things just any old place. In the lost zone, we don't want to invest in treatments that are designed to improve stands for the future. In other words, we don't want to do spruce restoration treatments in the lost zone. Salvage is fine if foresters are comfortable with getting regeneration that's necessary, but as far as other kind of investment in long-term spruce stands there, that's not the place. Threatened zones, we can do certainly resilience treatments or type conversion there, and the persistent zone is really the best place to do these salvage and restoration efforts, but the threatened zone should be considered too, and there's variability in there. And then in the emergent zone, we can consider planting as conditions change. So that pretty much wraps it up, and I want to leave time to address questions, but it certainly looks like a lot of this recent forest damage resembles early impacts of climate change, and you can argue whether it is or not, but I don't think that's where we should be focusing our effort. The point is, if we don't actively manage forest adaptation, we're going to have less in the way of ecosystem services that people depend on in the future. And I believe that using these, classifying the habitat into these change zones allows us to anticipate the change and focus the management where they'll be most efficient and most effective in the future. And the future has already arrived. So I will take a moment while you guys are coming up with some more questions and read through this Lorraine's question here.
Question. While Jim is reading through that,
I'd just like to add while we're... Go ahead, Megan.
I was just going to invite folks to participate in the polls real quick before anybody signs off, but I assume that you guys will probably all want to stick around.
Go ahead.
Hear Jim's responses to your question. So just a quick note.
Were you finished, Megan? Okay. Well, I can't really address your question too well, Lorraine.
I'm done. You go for it.
Biochar is not something I'm very familiar with, to be honest with you. And, you know, I think if we need to have some kind of disturbance, whether it's fire or mechanical, in order to regenerate aspen. That's clear. But if biochar does good things and it's, you know, the price is right, I guess there's no reason it couldn't be added to stands that have been mechanically treated, although it's probably not necessary in burn stands. Okay, Mike asking about female aspen clone. Well, aspen is dioecious, which means that an individual is one gender or the other, either male or female. So male clones obviously don't produce seed. So if you're going to try to treat aspen to create a seed source, you've certainly got to make sure that it's female first. There's other complications behind that because there are different, diploid and triploid aspen, and it's thought that the triploid aspen doesn't produce as much seed, so that could be a little bit of a challenge too. But we know that seedlings are getting established on their own, and you know, it may not be necessary to really do too much of this type of preparation, other than making sure there's disturbance at the where we want the seed to become established. Yeah. So thank you, Clifford. And Floyd, no, we don't have these on a website right now, but we are pretty far along into preparing a publication that is Jerry Rayfelt is, and we'll make sure that these things are certainly accessible. We have shape files and so on that we can provide to anybody that is interested come January. So you could send me an email if you're interested in getting that. Yeah, so Meredith is asking people to send her a private chat if you need continuing education credit from either of this. Thank you, Blakey. Looks like another... Looks like Paul's coming up with a question, or maybe he's just leaning on his keyboard.
All right. If there aren't, I'm going to see more. Maybe.
Okay.
Hey, Jim, I'm going to put your email up here, so if people have any
Yeah.
Further questions.
Paul raises a very good point about herbivory management, and it's I think it's varies tremendously in Colorado, at least, how severe that problem is and how much it impacts aspen treatments. And there's a variety of thoughts on it. I think you know more about this than I do, and I don't think anyone, the foresters don't necessarily have a plan for that, but they know where these things, where it's likely to be a problem and where it isn't. For instance, at Terror Creek, where I showed you that picture of the 35-year-old stand, that's an area that's been a kind of a aspen breadbasket for management for a long time, and there are patch cuts like that all over that watershed, and they've all regenerated great. Herbivory has not been a problem in there. In other areas, it's a big problem. So it's going to have to be addressed, obviously, where it is a problem. Fencing, I don't think, is a long-term economic solution, but there's thoughts about overwhelming the elk with sheer numbers of acres that are regenerated, and there's talk about managing elk numbers and managing grazing so that cows aren't doing it. It's a complicated problem. Yeah, so Brent is asking about how the breakpoints thresholds were arrived at. And I would have to say that the process that we went through is completely objective up until that point. The breakpoints and thresholds are certainly subjective, and we decided, for instance, with the 0.3, we wanted to be conservative on calling something lost, because that's, if you call it lost when it could be managed and protected, that's not good. The 0.5 has a little bit more objectivity to it in that it represents the balance between suitable and unsuitable. It's in the middle of levels, and it also is the best predictor when you use the reference climate period. It's the best predictor of where aspen is now. So it balances the errors of commission and omission, to use the modeling language. So that's about it. But, certainly people could use other thresholds, and that could be considered.
Looks like we have a couple more questions filtering in, and while they are, I just would like to extend a really big thank you to you, Jim, for putting this presentation together. I know I certainly learned a lot, and from the audience participation, it seems like everybody has also learned a lot also. Please keep your eyes out for a short announcement from us about upcoming webinars for 2015. My partner Meredith and I have paid close attention to the suggestions you all have made about potential subjects for future webinars. We're excited to be solidifying our lineup for the coming year. And with that, I'd like to remind you can find a link to past webinars, including this one, on our YouTube channel. I put that link in the chat pod. So for those of you that would like to stay tuned in, go for it. There are a couple more questions.
I want to apologize for my fluctuating voice.
Participating today for our Learn It Lunch
I got the
webinar. I'm going to hand it back over to Jim.
Headset that money can buy in Gunnison, but apparently not good enough. So Brennan's asking about the maybe buffers between the edges of the change zones. That's an interesting question. And I didn't really get into the level of uncertainty that is associated with these kind of projections. And I think you really have to view the boundaries between these change zones as very fuzzy ideas of where things might be suitable and unsuitable and so on in 2060. So I shouldn't think that you would be wanting to get too precise about this. There's a lot of uncertainty in the climate models. There's also the fact that we've just picked one point in time to represent as the future, the decade surrounding 2060, and obviously things are going to march on past that. So we picked 2060 because it's far enough in the future. It seems like a reasonable target time for when things that we do today will kind of reach fruition. But yeah, we do have to recognize that climate will continue to change after that, and so we just do the best we can to kind of keep up with it. But definitely consider these fuzzy boundaries, and also the time zone is not exact either. The decade surrounding 2060, depending on how good the climate models are, the things that we're projecting could actually occur in 2040. 2050, 2070, 2080. So there is uncertainty around these kind of projections.